Thanks very much. Okay, so next up we have my co-chair, Rosemay Killen, talking about the lunar sodium exosphere from ground-based observations.
Okay, what I'm going to be talking about is observations of the lunar sodium exosphere from a ground-based coronagraph that we built, and it's sited at the Weiner Observatory in Sonoyta, Arizona, and this is just a picture of it. This is a picture of our telescope. It's a very small telescope. It's only 10 centimeters, and what we normally it's closed up, but it's in this. Wanted to show you the components. So we have the telescope, and we have, in order to block out the moon, we have occulting disks, and then we have a very good CCD camera. We run at minus 40°C, and then we have a narrowband filter centered on sodium. So this is just the procedure. One of the first thing that we found out when we built this was that guiding at lunar rates is not adequate because the moon has a kind of a non-uniform motion. So we installed a very nice auto guider, and we auto guide on a small crater on the moon, so that during the 10-minute observation that we have to take to get the sodium, we very accurately track the moon. So in addition to the sodium filter, then we observe on-band and off-band so that we can subtract the continuum. And then we take the occulting disk, move that out so that we can take an observation of the moon. And the reason for that is twofold. Number one, we calibrate on the moon, and number two, we want to know the exact position of the moon during our observation so that we know we can get the profile of the exosphere from the lunar limb. So this is what my screen looks like. We observe from my office remotely. So every night that the moon is available, we look at the webcam, and if it's clear, we go out and observe. And so what you see in the upper left then is the image of the moon and the guider. And then, let me see. Okay, so this is the image of the moon. This is the image of the crater that we're guiding on, and so this is the auto guider image. This is the image of the exosphere with the occulting disk here. So in addition, we have the filters, we have the heater, because we want to keep the filter at 52 degrees for on-band and 40 degrees for off-band. This is mostly obscured, but that is running the telescope. That's the Sky software. Then we look at the scan across this image we want to know if the counts are very high, we know there's too much scattered light. What else? That's pretty much it. And then, so you can see the solar spectrum is in the black. Now this was taken at the McMath Pierce Solar Telescope at 20 milliangstrom resolution. This is our resolution of this instrument. So it's 1.5 angstroms, which is a fairly narrowband filter, but it's of course not as good as in a shell spectrograph. And our continuum is actually out there in the blue. So we switch from on-band, which is here, and then our emission is very narrow. So in addition to the sodium emission in this filter, we have continuum. And I have calculated the ratio of the continuum emission to the inside the narrowband filter to the continuum outside. But of course, in reality, it isn't always exactly the theoretical value. So I have to correct for that. Okay, so the data, we've gotten pretty good data this spring. We have lots of nights, and most of this is already reduced. We have quite a few corrections. Obviously, you have to flat field for the white light. We have to flat field for sodium. And then what we want to do is obtain the profiles all the way around the limb. And we have to calibrate. And I do that using the Hapke function. This is from Bruce Hapke's paper back in 1984. And so I've programmed up his equations and calculated the reflectance for each one of our phase functions. And I've calculated it for both the bright and the dark. And what I plan to do is calibrate using a bright Highlands reflectance and a dark Mare and compare the two just to make sure that I'm not getting any errors. So this is what we wind up with. You see, okay, with the occulting disk, this is the edge of the occulting disk here, and this is our emission. And then we superimpose the moon, which is taken at a different time. This is a superposition, so that you can see where the moon is during this observation. And that's important because what we want is to get the actual profile of the exosphere from the edge of the moon, which is here. And then, of course, this is the area in between the moon and the occulting disk. Now, what we've done over here is use a polar transform so that we can get the profiles quite easily across from the moon out. And this has been programmed up so that we don't have to do it manually, which takes a lot of time. So this is just showing different phase angles. Now what happens, this actually needs to be done over because if you get the center of the moon correctly, the edge here will be straight, and this isn't straight. So it really needs to be done over again with the exact center. You can also see that we have some ghosts in our system that we have to correct for. So I have a summer student this summer from Howard University who's done a lot of the reduction. However, what I'm going to do myself is the profiles and the calibration. I've already done the Hapke function for all of these phase functions, so it's just a matter of running a code. And here we are out at Sonoyta. We had to do some work on the telescopes. We went out there. And this is Tom Morgan and Roy Tucker. Roy actually works at the University of Arizona, so it's useful to have somebody out there every once in a while. Something goes wrong, or we need to change something out, and he runs out there and works on it for us. So I'll take questions. Yeah.
Yeah, I think there's all at high phase angles. I think the Hapke reflectance there's a roughness correction factor, of course, and I think it gets really dramatic at high phase angles, if I remember right. Do you take that into account when you do that?
Yeah,
that
I
surface
programmed
correction?
up the whole schmear. It's
Okay.
really quite complicated, but yeah, we do the roughness correction.
Okay, Jody, just behind.
So Rosemary, the Hapke function that you use, is that just a backup because isn't ultimately the off-band measurement you take, that's sort of the measure of the scattered light and hopefully it agrees with the Hapke function at different phases?
Yeah, that's for the continuum and for the bare moon. And like I said, it's quite different for the Mare and the Highlands. So you'll have the parameters for bright and dark, and I programmed them both up because I want to see if I get the same calibration using a Highland or a Mare. And I haven't done that yet, but I mean I've programmed it up, but I haven't done the calibrations, and hopefully they'll be the same or similar.
And one final note, is the ghost you showed in that one slide, is that not the shadow of the moon cast through the tail?
I don't think it's the shadow. I think it's caused by reflection off of one of the edges of a filter.
Okay. Any other questions? Actually, I've got a quick one. So, so how many nights a year do you get to make observations? Is the weather good enough?
Well, like this spring, we've had a lot of good nights. Last fall, the weather was terrible, and in the summer, they actually shut down the observatory because of monsoon. So, in the summers, we don't work. In the fall, typically Arizona weather is supposed to be good, but last fall, it was pretty bad. So it's spotty. And this spring, we did a lot. So.
Okay. I mean, have you got any plans to set up a similar telescope somewhere else so that you've pretty much got almost near continuous coverage of the moon in sodium?
Well, we don't, but...
No, I mean, if you had another observation site, hopefully between the two sites you'd get most nights. So no plans then? Okay.
No,
That's
no
a lot
plans.
of work, right?
Yeah, no plans to build another one.
Okay, all right. I think we're a little bit ahead of schedule. Okay, so, all right.